Have you ever just stopped and wondered about that? I mean, really thought about it. What unseen orchestra is conducting the entire universe, making a ball fall down, a huge ship float, and our planet spin around the sun? Well, it turns out there are rules, incredibly powerful, fundamental rules.
So let's dive right in. In this explainer, we're going to get into the fundamental forces that dictate every single push, pull, and interaction in our world. We're going to pull back the curtain on the physics of motion itself.
So here's the plan. We'll start with the forces we can literally feel, the forces of touch. Then we're going to venture into the more mysterious stuff, the forces that work across empty space. And finally, we'll see how a little bit of math brings all of this into crystal clear focus.
Okay, first up, contact forces. These are the ones that just make sense, the forces that happen when things are physically touching. I mean, think about it. Almost every single thing you do all day involves direct contact.
So, why aren't you falling through your chair and the floor and the center of the earth right now? The answer is something called the normal force. It's the upward push from any surface that's holding you up, and it always acts at a perfect right angle, or normal, to that surface. It's basically the universe's way of saying, nope, two things can't be in the same place at the same time.
All right, next up is tension. This is that force you feel in a rope during a game of tug-of-war, or maybe in the straps of a really heavy backpack. It's a pulling force, and it travels along the whole length of a string or a cable, always pulling away from whatever it's tied to.
Now this is where it gets interesting, because friction really has two different faces. You've got static friction, which is that stubborn force that keeps something from moving in the first place, when you're trying to push a heavy box. Then there's kinetic friction, and that's the force that resists the box once you've already got it sliding. And get this, static friction is usually stronger. It almost always takes more of a shove to get something moving than it does to keep it moving.
This one is basically the force of snapback. Anytime you stretch a rubber band or jump on a trampoline or squish a spring, there's this other force that's fighting to pull or push it right back to its original relaxed shape. That's the elastic restoring force.
And there's a beautifully simple piece of math behind that snap. It's called Hooke's law. All it says is that the restoring force, F, is equal to how stiff the spring is, that's the K, times how far you've stretched or squeezed it, which is the X. And that little minus sign, that's the most important part. It tells us the force is always fighting back in the opposite direction of how you moved it.
So why do these massive steel ships weighing thousands of tons just float? Buoyancy. Yeah, when an object is in a fluid, like water, the fluid actually pushes up on it. This upward push, the buoyant force, fights against the object's weight, and that's exactly why you feel so much lighter in a swimming pool. It's all about how much water you're pushing out of the way.
And last but not least for our contact forces, we've got drag. This is that resistance you feel when you stick your hand out the window of a moving car, right? Or when you try to run through the water at the beach. That's the fluid, the air or the water, pushing back against you as you move through it.
Okay, now we're entering a totally different realm. These are the forces that don't need to touch anything at all to have an effect. They act silently, invisibly, across huge distances, shaping everything from the tiniest atoms to entire galaxies.
Gravity, right. We all know it. But it is so much more than just what makes an apple fall. This is the grand architect of the entire cosmos. It's the force that pulls giant clouds of gas together to light up stars, and it holds galaxies with billions of those stars in its grip. Here on Earth, we just give gravity a more familiar name: our weight.
You ever rub a balloon on your hair and have it stick? That is a tiny little glimpse of the electric force. Now, unlike gravity, this one can both attract and repel. And on a small scale, it is unbelievably, mind-bogglingly strong. In fact, this is the force that holds atoms themselves together. It governs all of chemistry, all of biology, every reaction, every bond is all thanks to this one fundamental force.
And rounding out this amazing trio is the magnetic force. And it has this one fascinating quirk. It only affects charges that are moving. It's the silent power that makes electric motors spin, sure, but it's also Earth's invisible shield, protecting us from solar radiation. It's the inseparable partner to electricity. And together, they form electromagnetism, the engine of our entire technological world.
Okay, so these forces aren't just vague, cool ideas. They are incredibly precise. They're predictable. So now we're going to see how physics gives us the tools to turn these powerful concepts into actual concrete numbers that we can work with.
So let's calculate the friction on that sliding crate we talked about. First, we figure out its normal force, basically how hard the floor is pushing back up on it, which is 98 newtons. Then we use this thing called the coefficient of kinetic friction, which is just a fancy number that tells us how grippy the surface is. For this one, it's 0.3. We just multiply them together and boom, the floor is resisting that crate with exactly 29.4 newtons of force. Simple as that.
And what about that spring? Well, the spring constant, or K, is just a way to measure its stiffness. Let's say it's 150. If we stretch it by 0.2 meters, Hooke's law gives us an answer of negative 30 newtons. And remember, that negative sign is just telling us the spring is pulling back with 30 newtons of force, fighting against the stretch.
Calculating weight is actually beautifully simple. You just take an object's mass, in this case 7 kilograms, and multiply it by the acceleration due to gravity, which is a pretty steady 9.8 meters per second squared here on Earth. That gives us a weight, or gravitational force, of 68.6 newtons. Now, even this invisible force can be pinned down. We use something called Coulomb's law. It might look a little complicated, but really we just need to know how strong the two charges are, how far apart they are, and a special constant. You plug those numbers in, and you find out the force is 5.4 newtons. It's just incredible that we can so precisely measure these unseen interactions.
And that really brings us to this powerful idea from Galileo. These formulas we're looking at, they aren't just random equations in a textbook. They are literally descriptions of the fabric of reality. This is the language of the universe.
So, let's just do a quick recap. We've seen that pretty much all motion is governed by two main kinds of forces. You've got your contact forces, which need to physically touch, and your field forces, which can act from way across the room, or the solar system. And maybe most importantly, we've seen that these powerful, world-shaping forces can be understood and even calculated using these clear, elegant mathematical laws.
And that leaves us with one last thought. These classical forces, they do a phenomenal job of explaining our everyday world. But they aren't the whole story, not even close. So what mysteries lie in the gaps? What happens down at the quantum level, or deep inside a black hole, where these rules just completely break down? The search for those answers, well, that continues.